Thank you for joining us today. I am here with Dr. Yevgeniya Leonova, who we call Jeannie. She's been working with us here at Deep Future Analytics for about 5 years, if I have that right, Jeannie?
Yes, I've been around DFA since 2015, so it's actually more. It's 7 years.
Very good. Okay, so thank you all for joining. I know some people are still coming in, but we'll go ahead and get started. Jeannie has been doing a lot of work on machine learning and how one combines that with vintage analysis in order to do long-range forecasting. So she's going to present work that she and we here at DFA have been doing. Jeannie, if you want to go ahead and share your screen.
Mm-hmm. Good afternoon or good evening, everyone. Today we're going to talk about how to guide AI and machine learning algorithms through the economic cycle. And I'll be presenting on behalf of myself and Joe. We did this together. I'm sorry, how to? Sorry, I'm trying to start with the first slide here. It doesn't work. Okay, thank you so much. So a short overview of the talk. So today we are going to talk about the cases when big data is actually only a little data, and what it means in case when we want to use long thin data and to build long run model. So we are going to talk how to combine long run model with so-called in our industry scoring models. And in particular, we are going to talk about the certain type of long run models that we call vintage models, and how to combine this with machine learning methods popular right now, like neural networks and XGBoost. And we are going to present an example that we built as a proof of concept on US mortgage data. So when big data is only little data. Many of high-tech companies right now, like Google and Amazon, are leveraging a massive amount of data. And the algorithms have been here for a while, like machine learning algorithms have been since 60s, 70s, and 80s. But right now they're gaining a new life due to a massive amount of data and also computational resources provided. But actually, what we call big data is actually a really short slice of history, especially in banking industry. So we in retail lending, we almost never see a data set that we would call big data that goes back to a recession of 2009. In fact, what we have in terms of time, we have only a short slice of history. So what we actually have, what banks provide us is very basic information like defaulting accounts or attrition accounts. And basically what we have for every account is product, time of attrition, time of default, and origination date. So that's the information that we can use to build a long run model. We call it long thin data. But big data have more specific information like behavioral characteristics and basically information on the individuals. Okay, so it means that we need different types of models for these different types of data. So what we want is to use both data, both long run data and big data. We are going to, so the thing is to start with a long run model and then use that and then combine it with neural methods for machine learning to use both of them and to steer it through time. So how to combine long run model with scoring models? Scoring models is just a name for the machine learning algorithms that we use. So the procedure has a two-step approach. First, we're going to use long thin data, and here we usually have 20 years of history or more, like several decades of this basic information. And so we are going to feed that into the long range model, the methods that have been around, to create a long range model, basically the long range forecast. And so we are going to use this long range forecast as an input, fixed input to machine learning algorithm, together with big data that we have to produce a forecast. So, and the keyword is there, fixed. So fixed input is a certain jargon for our industry. It means that we have, in our machine learning method, we are going to use coefficient, an input coefficient for a forecast produced from long range model, and the coefficient will be 1.0. So in other words, what it actually means is that our machine learning algorithm will be will learn the residuals of relative to the long range model. and independent on whether it's how does the output variable looks like. So in other words, we don't want machine learning method to second guess a mean of the distribution going forward. What we wanted to be, we wanted to learn around the account variation of this mean produced by long range model. So as at the end, our forecast will look like machine learning plus the output from the forecast from machine learning algorithm plus the output from the long range model. So how to combine long run models with scoring models? And we are going to start with one of the long range models called APC. And so age period cohort models have been around for a while. They were developed in 1897 by a psychology professor in Germany. And the basic idea is that any temporal change can be attributed to three kinds of processes. The first one is the change of over the life course of an account. We call it age effect. The second one is the change due to the replacement of older cohorts with newer cohorts. In our case, it's we call it credit risk function. And the last one is the change due to the certain events in particular years. In our case, it's economy shocks. We call it environment function. So on the pictures here, you can see decomposition into this three function of probability of default, the log odds of the probability of default. And this came from Freddie Mac mortgage data. So Joe actually never mentions that, but he was the inventor. He was the first one who applied this in a credit risk modeling. So he can tell you the story of how he came up with this. But again, so the idea is that we take the vintage level data, and by vintage, I mean we call a vintage a group of accounts that were originated in a certain window of time. So in our analysis, we were using monthly data, but you can do it with any kind of window, like weekly or quarterly. And so we take the aggregated vintage data and we compare every vintage, every cohort, say what January 2017 cohort looks like in terms of performance, and how it can be compared to other cohorts. And in that comparison, we are going to assume that the formula at the bottom is true. So the log odds of probability of default, PD, can be represented as the sum of three functions. The life cycle function here versus the age of the account, the credit risk versus the cohort or vintage date, and the environment function. So to stop at every one of this life cycle function here, actually it's in the probability scale. So what you actually see, the y-axis is of probability, conditional probability, which means that we are looking at the default rate on a certain date, but only among those accounts that are active on this date. So this can explain why this function goes up. So why the probability of default goes up with when age increases, even though the amount of accounts in a cohort goes down. The second function is credit risk function, and it's in linear scale, which here, so the central line is 0 here, which means that it's additive to the life cycle, to the log odds of the life cycle function you can see on the first picture. And so positive values of credit risk function means that it the vintages that have higher risk comparing to the average. The lower values represent the lower risk compared to the average. And Joe actually has a research where he shows that this function follows like a little bit of what we call counter-cyclical, which basically means that banks usually book their worst accounts right before the recession, and the best accounts during and after the recession. So the third function is, we call it environment function, which basically shows the economic shocks. And again, it's additive here. Again, you can see the central line is 0. And the period of time where we have higher values means that it's more default accounts, and this basically is a recession. The lower values mean that and show that this is the good times, or basically the best time of expansion. So after we decompose that, we need to create a forecast. So to create a forecast, we need to extrapolate the environment function into the future using economic factors. And again, Joe has a research paper how to do that. But then after we extrapolate that, we add this to the credit risk for a certain vintage and life cycle. That's how we get the vintage level forecast, which means the average probability of default monthly for a certain vintage. And so the second step here is we're going to throw away the vintage function, and we're going to replace it with a machine learning algorithm. So no audio. Can you hear me now? Okay, sorry for that. So we're going to get rid of the vintage function here and replace it with a machine learning algorithm like neural network. And I'm not sure why it's not showing. Okay, so life cycle and environment functions are still going to be an input, but instead of the vintage function, you can see it in the formula at the bottom. We're going to use the neural network in this case. So this neural network is going to learn on our big data set. The network architecture would look like that. On the right, where on the right hand side, you would have all inputs, all behavioral and transactional inputs from the big data you have. Feed forward kind of network information would go towards the output node. And on the left-hand side, we would have this one single node containing the value, which would be the sum of life cycle and environment function for every month, every single account. And the weights for this single node should be 1.0. Now, there are packages in R that can do this, and in fact, we did that and we proved that it works. But we're going to concentrate more of XGBoost today. And so same thing, but instead of the vintage function, we are going to replace it with XGBoost method, which basically an ensemble of gradient boosted trees. It's been popular for a while, and so let's just look at the results we have for US mortgage data using XGBoost algorithm. We were using Freddie Mac data, which started in 2001 through 2009. We didn't use any data after during the recession, current recession, COVID, because it's just there are too many anomalies there, and there were over 1 trillion of mortgages. And we were interested in comparing actually our APC plus XGBoost with multi-horizon survival model. So you can find information about multi-horizon survival model following this paper in parentheses, Britton and Crook, dated with 2020. I should say that in both of these models, we actually built a separate model for every horizon. Now, why we did that is due to delinquency. So delinquency is very dynamic. So if you say have a delinquent 3 months delinquent account today, a peak of default risk for this account will be 3 months into the future, considering that for mortgage, we define default as 6 months delinquent. And so the same way for every other delinquency, and from 1 to 5. So it means that delinquency is highly nonlinear when we look at this over the horizon. So horizon into the future. So the next slide shows our results. We made did three kinds of tests in sample, out of sample, and out of time, out of sample. So in sample test was done over 3 years of data from 2017 until 2019. You can see the results here are good as was expected. And APC plus XGBoost model performed a little better than multi-horizon survival model. The out of sample test is on the same period of data, but on different sample, is almost the same, which again is was acceptable. And out of time, out of sample tests were performed on the data on the 2 years before training period. So it's going to be 2015, 2016 data. And you can see that AUC and Gini characteristics dropped a little. And what's interesting that even though the multi-horizon survival and APC XGBoost are very close, and they are even inside the confidence intervals of each other, but APC plus XGBoost model shows are a little better and shows consistency in this regard for every of these 3 tests. So even though ROC curves are important, they only show how well does the model rank every single account between themselves. But one of the other validation tests is actually to look at the aggregated forecast that the model produces to make sure it's not biased, because it can still be biased even though ROC curves perform well, show good results. So same kind of forecasts, 3 forecasts, but we are looking right now at the time series aggregated forecasts. And so this peak here around 2018, this is consistent, and both models, you can see that over predict this compared to history. So black line is the history here, and it's just a glitch. We think that there was a change in policy here, because it looks like there were lots of delinquent accounts that were supposed to roll to default, but it didn't happen due to policy change. And so you can see that the models here are almost identical. So they almost show the unbiased results, except maybe this period of time at the end for gradient boosting. And I actually forgot to mention that we gradient boosted trees, we were using stochastic variation of this. It means that at every iteration of training, we would take a random sample, and train on that rather than using the whole data every time. It just to make sure that we are not stuck in any local minimum. And the second test, the third one test is out of sample, out of time, actually, where gradient boosted trees performs a little better, even. So it looks like it just it just make use of all the make more use of the information, all that behavioral information we're giving. So I guess that was the last slide.
That's great. Thank you, Jeannie. We're getting some questions, and and I'll remind everybody we have time here, that if you want to enter questions in the chat, you can do that. So let me look through these quickly. One of them, back on your vintage decomposition slide, it showed a deterioration, it looked like, in the credit quality over the last couple of years. And so the question is, do we think mortgage originations got worse in the years leading up to the pandemic, because this data ends right before the pandemic?
Now, I'm not sure about that, because, well, usually, so in cases like that, this tail that we have in credit quality means that it's very young vintages, so we don't have much data on those. So sometimes it may be due to just because of this, you can question the tail there. Maybe Joe, maybe you have.
Yeah, I agree. And you do see, though, a long trend starting back around 2015 of worse quality originations. And I think it's hard to know in the most recent year or two exactly how bad they are, but I think there isn't much doubt that people were getting more lax on originations in the years 2015, 16, 17. That period is definitely trending up, and for that we have pretty good measurements at this point. Now, what's happened since the pandemic is probably much more volatile, and Jeannie, I think it's the case that Fannie Mae and Freddie Mac haven't released any data on the most recent couple of years of originations. Is that right?
I think that's true.
So we don't know yet. Okay. And then another question that came in was regarding how similar the results were for the multi-horizon survival model, which is basically vintage plus logistic regression, as compared to the vintage plus machine learning approach. And I'll go ahead and offer that I think the issue here is that the data that we get from Fannie Mae and Freddie Mac is actually not very rich. It's a very limited set of performance indicators. So machine learning models are being used in cases where the data is highly nonlinear. And that can mean that In other cases with more complex data sets, there may be a greater distance between a machine learning approach and a more linear approach. But in kind of traditional data sets like the mortgage data we get from Fannie and Freddie and bureau data, there probably isn't a great deal of separation between what machine learning can do and what a more I call it linear, but really the multi-horizon survival model is it's a combination of nonlinear effects like life cycle and environment with some regression modeling. It's a quote linear model, but actually a rather flexible one. So I think it's more about the data coming in. Does that make sense, Jeannie? Anything that you would add there? In fact, Jeannie, I know that you've worked on more complex data sets for other clients in this kind of machine learning plus vintage analysis. Did you see, can you speak to any similarities in performance there?
You mean as comparison with multi-horizon survival, or?
Yeah, I don't remember if you used a multi-horizon survival model, but I know you had a more complicated.
I actually, can you hear me now? So I actually compared APC plus XGBoost versus just XGBoost, but using vintage date as an input and also age. So those two show on a different data set, which was much smaller than mortgage data, which could affect the performance, of course. So those two were very similar. But a good thing about APC plus XGBoost was that it learned much faster comparing to just XGBoost, because we already start with a good approximation, which is our long run APC model.
That's an excellent point, that if you just turn XGBoost loose on loan performance data, it's going to use trees to try to understand the embedded life cycle and environmental effects. And those are more continuous processes. You don't really need a tree to understand those. So that makes a lot of sense. I see a hand raised. Jared, I'm going to let you unmute and ask a question if you've got one.
Yes, thank you. On this page showing the discrimination tests, is this comparison, this is the joint outcome of all components of the models, right? This is not a comparison of, say, XGBoost and the logistic, air quotes, linear model component, right? This is showing me the combination of
Right, this
the
is the
APC
combination.
and environment. Okay.
Yeah, and I forgot to mention that this is actually the all horizons together. So we combined all horizons together, and the output variable here is the monthly probability of default. So you compare, it's not like it's cumulative probability during this period of time, but monthly. So
my one comment is simply that that frame makes a lot of sense, right? Because the object of interest is a monthly default rate.
yes,
However,
yes,
the inclusion of the environment and the vintage or life cycle functions probably induces a lot of commonality between the two experiments. And if you were to strip this down to kind of the scoring or the cohort dimension, it might tell you, be a little more informative about just how much improvement or difference there is between the two methods, because really you're only substituting in for 1/3 of the APC function, this ML model, right?
Well, right, but in this case, I wouldn't, in ROC curves, you have to compare with, so the score you produce or the your forecast with some output variable. So I wouldn't, I'm not sure which output variable I would use to compare it this just with an output of machine learning part of equation, or scoring part of the equation in case of multi-horizon survival model. I'm not sure.
I think you're right. You would need some kind of a synthetic output as the target that would take the real numbers and adjust for life cycle and environment.
Yeah.
You have to have those somewhere in order to explain what really happened. Now, that does mean that it's worth saying, this is using the real environment function. So this is an ideal situation where you know what the environment's doing. There is a separate degradation that occurs in the future if you have to make a model and guess a scenario and have an economic model that predicts that environment function. So we're separating effects here in the sense that this is showing the ideal performance where you know what the economy is doing. If you have to use an economic scenario, it's going to degrade by as far off as your economic scenario is. And that's kind of our usual way of testing things. Okay, thanks for that question, Jared. And so any other questions, or either by raising your hand or by chat? And anything else come to mind, Jeannie, that you would add here?
I'm not sure. Maybe you have some additional information.
Well, I think if no one else has questions, I'll wrap up by pointing out that, as you can see, we do a lot of work in this area. And we actually have been doing a lot of work recently in validating machine learning models, establishing best practices for how to do that, how to make it fair to compare a machine learning and a linear model from a validation perspective. So, small bit of advertisement is that if you need any assistance either in incorporating machine learning techniques, building models like these, or doing model validation, we're happy to help with any of those things. So if we have no further questions, I thank you all for your time today. And in about 1 month, we will have Dr. Nick Dobranoff presenting some of his work, which is related to model selection error, looking at the error that comes from the process of choosing one out of many candidate models, and what we can say about that. It's very interesting results. So I hope you can all join us for that as well. And the registration is on our website, just as it was for here, deepfutureanalytics.com/events. So hope to see you in a month. Take care, everyone.